Graph rewriting is a pretty popular area of study for procedural content generation in games because it allows for a high level of flexibility and customization beyond what other simpler, more common techniques offer. The concept is so flexible, in fact, that just in the game dev space, it's been used to generate level maps, quest structures, building geometries, and more. This technique and variations on it has been used in games such as Unexplored, Lena's Inception, and Enter the Gungeon. So in this video, we'll look at what graph rewriting is and how to use it to generate procedural content. But first, just in case you're unfamiliar with the concept of graphs or maybe just need a refresher, let's do a quick review of the data structure behind it all. A graph is a data structure that consists of two types of components: nodes, sometimes also called vertices, and edges, which are used to connect nodes to one another. There's a large number of classifications a graph can fall into based on its structure, specialized algorithms for dealing with certain types of graphs such as trees, and multiple ways of representing the data. But we're not really interested in most of that today, and all we care about for this intro section is the concept of nodes and edges. Nodes can be connected to as many or as few other nodes as we want, and even connect to themselves if desired. Edges can have a directional component to them, i.e. you can only go one way from this node to the other, or they can be non or bidirectional. For today's discussion, we'll also assume that all graphs discussed are connected graphs, meaning that there are no gaps in the graph and that every node can be reached by every other node by traversing some set of edges. Graphs are used in a lot of different applications. On social media, users can be represented as nodes and followers represented by the directional edges between users, thereby showing who follows who. In pathfinding algorithms, nodes can be the potential waypoints you'll travel through, with edges representing which waypoints are connected to which, and even a state machine diagram is really just a graph with directional edges. But hopping back to the pathfinding example, this is kind of a big deal for game dev purposes. If we represent each area of a level as a node and use edges to denote which areas connect to which, we now have our level represented in a very algorithm-friendly way for further processing. Snap everything to a grid, maybe throw in a few constraints to prevent any wonkiness, and you've even got yourself a grid-based dungeon layout ready to be thrown into your favorite tile map. But it's not really that interesting to just show you a data structure that can represent a level. We need to do something with it to make it worthwhile, and that's where graph rewriting comes in. With graph rewriting, we generate a starting graph and then process it according to the rules we define to rewrite parts of the graph, typically iterating over the graph continually in case one rewrite triggers the rules of another until some condition is met or there's nothing left to rewrite. If you've seen my video on generative grammars, this should sound very familiar to you, as it's the exact same technique we discussed then, just being used with a different data structure. The rules for rewriting can be whatever we define: swap one node for one or more nodes, replace an entire subgraph, delete nodes, or even just shift things around. We'll simply code up our algorithm to look for a pattern and then process it accordingly once found. And since I think visuals can really help drive home how this works, let's take a few examples to see what rewriting can look like. So here's our starting graph that we'll use for all these examples. In this first rule, we'll simply say that all blue nodes should be replaced with a green or yellow node. So we'll write an algorithm that scans the graph for blue nodes and swaps them with a randomly selected node from the available choices, making sure to maintain all edges and connections the original node had. And in this example, we'll define two rules. One to replace any pairs of blue nodes connected to purple nodes, and another to replace a pair of two purple nodes connected together. When we scan our graph, we'll first find a match for the blue-purple pair and replace it with its appropriate replacement. When we scan the graph again, we'll now have a match for the pair of purple nodes and swap them for a green and purple node. And lastly, just to show you that it's not always a complete rewrite, here's a rule where we simply shift a collection of nodes around when a pattern is matched and adjust the connections provided as necessary. And that's graph rewriting in a nutshell: a collection of patterns to look for and rules for how to replace them. The rest is up to you to define, but you may be wondering how you even get the starting graph to work with, and there's a few common options. One approach, such as used in the MetaZelda algorithm, is to first generate a tree, storing metadata about the generation process at each node, and then randomly connect neighboring nodes to one another that meet certain conditions. These conditions can be things like only connecting nodes that have a similar difficulty level, similar or at least compatible key or item requirements, and so on. The nice thing about the tree structure is that you can track how deep each node is in the tree, making it easy to add lock and key puzzles, adjust difficulty based on player progress, and know where a good spot exists to put more valuable loot or even the end of the level. Another option is to do what is essentially a random walk by placing a starting node, adding some nodes and connections to and around it, moving to another node, and repeating until you have a graph of the desired shape or size. And lastly, and the technique you may be most interested in for having a bit more of a crafted experience, would be to manually define one or more graphs to start with and use that to seed the rewrite. If you're generating a dungeon, for instance, you may want to start off with a graph that has entrance and exit nodes and let the algorithm fill in the details. For generating a quest, you could define a few basic beats you want it to have, and so on. And so now that we know what the process of graph rewriting looks like, let's take a bit deeper look at what we can actually do with it. But because this technique is so generic, you can go a lot of ways with it, so just consider these examples as a starting point. The first area of generation, and what graph rewriting is probably most commonly used for, is to do level generation with it. And while grid-based level layouts are very common in games with procedurally generated content, it is possible to take a connected graph of just about any shape and turn it into a topologically consistent space. Most examples I've seen of this use physics simulations to achieve this goal. They'll start out by placing each node far apart from each other, and then apply spring-like forces to each node to pull it towards those nodes it's connected to, while simultaneously applying other forces to push all nodes in the graph away from it by a certain amount. This lets it have its own area in the game world to itself to carve out a room or other playable space. Once the simulation has run long enough to stabilize, you've got your level laid out and can connect your spaces with tunnels, hallways, and other connecting glue. With a grid-based dungeon, we can use our nodes to represent rooms and snap them to a grid position, tracking what cells have been used so that we can only place new nodes in unused grid cells. Once the graph is ready to go, we'll translate our nodes directly into rooms on the grid and place doors wherever our edges are. Another use of graph rewriting is to generate missions. Similar to graph grammars, we can have each node represent a step in the mission to complete, but with a data structure that is much better equipped to handle branching and conditional paths. Plus, once you have a mission structure together that you like, you can then run it through another rewrite system to turn it into a playable space, therefore really making the space and mission work together. I talked about this type of content generation a lot more in my graph grammar video, so check that out if you want to get more ideas on mission generation. And that's a quick look at graph rewriting. It's a really interesting technique for procedurally generating content for your game with a lot of flexibility to it. Check out the description for some great links about this technique if you want to learn more.